Now, in the remainder of the chapter, we just touch on a few interesting topics to spread the discussion just a little bit. And the first is robust statistical techniques. We've mainly been using a very standard statistical model, which assumes that populations are normally distributed and we have random sampling from those populations. But the world isn't always like that. It's true that the central limit theorem helps, even with moderately non-normal populations. Often we can still use our standard techniques because the sampling distributions will be very close to normal thanks to the central limit theorem, and that's what we need for our standard techniques. But not always. And statisticians have come up with a range of techniques called robust techniques because you can knock around the standard model a bit. For example, there are techniques that don't require the assumption of a normally distributed population. And this ESCI page supports just one example of that for independent groups, and is based on trimming of data from each end of the distribution. So even if you've got very funny shaped tails or long shaped tails or lots of outliers out there, well, if we trim them off, then we're left with a much better shaped or much more tractable data perhaps. So let's turn to ESCI and see what Robust 2 offers. I'm at the Robust 2 page, and I'm just going to say a very few brief things about this robust analysis, appropriate when we've got independent groups and what look like data coming from a non-normal distribution. And these are British data for stated number, claimed number of sexual partners in young people, males and females. And we've clearly got some very large outliers, particularly amongst the males. We can turn on a second display that gives our familiar difference axis and confidence interval on the difference axis, and clearly using a conventional analysis we've got very long confidence intervals. Now if we do a robust analysis here, note incidentally that the scale here is deliberately different from here because often we get quite striking differences in what we need to plot. In the robust analysis, we have trimmed off 20%, and you can adjust the amount of trimming here, and the trimmed data points are marked by X's, the retained data points by the red circles. So we started off for the males with 51 cases, we trimmed 10 off each end to finish up with 31, and here is the trimmed mean of the remaining 31, and the standard deviation appropriate for calculating this confidence interval with the trimmed data. It actually responds to all 51 data points. And so here we've calculated our mean and confidence interval to estimate something different, not the mean of the population, but the trimmed mean of the population. And that may be what we would really like if we think in the population that the extremes, the tails, are somehow not our primary interest, that they're contamination, that they're there for some strange reason, and we really want to focus on the centre part of the distribution. Of course, outliers sometimes can be a big part of the message, so we need to be very careful about trimming. But here we have a robust technique that gives sensible means and confidence intervals for 20% trimming. And you can go backward and forward and compare the two and work through and see how, if we do not assume variances equal in the conventional analysis, how that compares with the robust analysis with various levels of trimming. So there's plenty of scope for you to explore there, but the major point is that there are further techniques available. So if you run into data that looks really weird like this, then it's probably worth seeking expert consultation, because there are more complex techniques that might be appropriate for the sort of data, the sort of questions that you have. Finally, we could have chosen a dozen or more interesting future directions for development, and each one we hope would have given a really interesting story to spark your interest in, oh yes, research can explore wonderful things and discover wonderful things and explore really interesting questions. And second, to see just how broadly the general principles we've been discussing all along, open science and so on, apply, sometimes in slightly different ways, sometimes not absolutely every aspect of what we've been discussing, but you have to consider all the open science issues in all these future directions we consider. So archival data is data already existing, maybe in a large, highly valuable existing database. Longitudinal data can be terrifically valuable to collect data over decades about how people develop and change in various situations. And our example combines those two. Numerous DVs, so think of genetics and think of brain mapping, where we don't just get 1 or 2 or 3 measures, but you might have thousands or tens of thousands of measures, and we need to estimate the sizes of effects in perhaps groups of DVs. So some of our basic logic applies, but we also need to come up with new techniques, but we need to be very, very careful of seeing faces in the clouds, and the dead fish experiment gives a cautionary tale there. And then the final thing we mention is big data, the sort of massive data sets that you can collect online with lots of people or on your mobile phone over a lot of time, and the approaches to setting up big data experiments that might be able to collect large amounts of data and answer very interesting research questions by using your ingenuity. Again, of course, you'll be very careful about planning and pre-registering and trying hard to avoid cherry picking. Do you dream about these pictures yet, these moving pictures and dances yet? I hope so. Can you bring to mind the cat's eye, the forest plot and the diamond, the difference axis and the confidence interval on a difference, the dance of the confidence intervals, the dance of the p-values, all in the context of open science, the way I'm sure you will go ahead and do science. May all your confidence intervals be short.